With the aid of the James Webb Space Telescope, the most potent telescope currently in use, speculated about what life would be like on distant planets. Finally, the answer to that issue can be found by watching Proxima Centauri, the star system that is closest to us and is only 4 light-years away. Researchers have observed some oddities coming from Proxima b, one of the planets in the system. The brightest minds in science have been perplexed by these abnormalities, which are known as artificial lights. However, what are they? Do these lights point to the possibility of sentient life on Earth? Come along as we examine the startling revelation of city lights made by the James Webb Space Telescope that alters everything. As far as we know, there is only life on Earth. People have wondered whether there is life elsewhere in the universe ever since civilization began. The search for extraterrestrial intelligence, SETI, project was started in 1984 by American astronomers Jill Tarter and Thomas Pearson to conduct just such an interstellar search. The nonprofit's goal is to collect radio signals from space because, due to their longer wavelength, radio waves are more likely to be picked up by the 42 radio telescopes that comprise the rare Allen Telescope Array in the Cascade Mountains of California. Radio waves are perfect for this search since they are less absorbed or distributed than other forms of radiation. But no authentic alien signal has been found in the last 30 years. Following that, the successful launch of the James Webb Space Telescope aided in the investigation of a number of remote, unexplored planets around faraway stars. With its highly sensitive detectors and floating around 1 million miles away from Earth, the world's largest telescope is poised to yield important findings. More than 4,000 planets, also known as exoplanets, have been found orbiting other stars since the discovery of the first known planets outside of our solar system 20 years ago. NASA estimates that there could be trillions of exoplanets in the cosmos. Alien plant life may contain the first indications of life outside our solar system. While its route to Jupiter, the Galileo spacecraft turned its instruments back toward Earth and discovered a clear hint of plant life. The vegetation red edge, VBI, signature, which is a combination of red and infrared light reflected by plants, was picked up by the sensor. A planet like Earth, for example, with its jungles should have a strong and easily identifiable VBI signal. The VBI of distant, Earth-like planets in the habitable zone surrounding stars will be measured by the JWST, and this data may reveal crucial indicators of life in the exoplanet atmosphere. The JWST might be able to track sunlight as it enters a planet's atmosphere and crosses its star. Spectroscopy, in which particular wavelengths are absorbed by atoms and molecules in the atmosphere to produce a distinctive fingerprint that the JWST can detect, would then be used to find the light's missing wavelengths. The composition of the atmosphere and the locations where life is conceivable can be ascertained using this technique. It is possible that life may exist on planets the size of Earth that have atmospheres like our own, which are mostly composed of carbon dioxide, nitrogen, and oxygen. It can be possible to identify technological life by searching for components that aren't often present. Aliens seeing Earth's atmosphere from a distance would likely notice the presence of chlorofluorocarbons, CFCs, which are produced for use in cleaning supplies and refrigeration. CFCs in planetary atmospheres would be a blatant sign of civilization if the JWST discovered them. It's interesting to consider that life on exoplanets may not resemble life on Earth at all. Even life on Earth, such as extreme species, might appear foreign at times. These creatures, which are mostly bacteria, can survive under conditions that would kill other living things. Some of them can withstand temperatures as high as 250 degrees Fahrenheit, while others can handle harsh acids with pH values lower than 3. It could be wise to start with Earth-like worlds first, even though life is more likely to exist there than on planets with extreme heat or acidity. It is possible for prime candidates to circle a stable star at temperatures high enough to support liquid water on their surfaces. Our Sun is classified as a yellow G-type star, which are less frequent and usually have shorter lives in our universe. Consequently, there is a greater chance of discovering planets circling red dwarf stars, which are more common and have temperatures and luminosities lower than the Sun. The genesis of life and the evolution of complex life forms are given extra time by these stars. The initial mission of JWST will focus on the TRAPPIST-1 planetary system, which is located about 40 light-years from Earth. It is centered around a quiet red dwarf star that has 7 rocky planets the size of Earth. Liquid water may be present on the surfaces of 3 of the rocky planets in the so-called habitable zone. Because of its planets' close orbits, the TRAPPIST-1 system emits light similar to Earth's, but having a considerably smaller and cooler mass than our Sun. The closest red dwarf star to Earth, Proxima Centauri, is 425 light-years away from the Sun and offers the best possibility for humanity to glimpse city lights outside of the solar system. A planet must be 20 times closer to Proxima than Earth is to the Sun in order for it to host liquid-based life, as Proxima is approximately 600 times fainter than the Sun. A planet with 1/3 of Earth's mass was found by astronomers in August 2016 in this habitable zone, which resembles a Goldilocks zone where the amount of light is just right for liquid water to exist. Proxima b may be an airless, lifeless planet, even if it orbits Proxima Centauri. Proxima b is in a close orbit that exposes it to strong solar winds that can completely destroy its atmosphere because it orbits its red dwarf star Proxima Centauri at a distance of only 46 million miles, which is significantly closer than the 93 million kilometers that separate the Sun and Earth. Proxima b receives enough sunshine to maintain Earth-like temperatures and liquid water in spite of this. Proxima b is believed to be tidally locked, meaning that it always faces the same direction toward the star as the Moon does with respect to Earth because of its closeness to it. With a mass of roughly 18% that of the Sun, Proxima Centauri burns significantly less brightly than one might expect for a planet that close to its star. Relative to Earth, it should be a red-hot cinder, receiving only 5% of the Sun's distance. Assuming Proxima b has an atmosphere to retain heat, liquid water might readily exist there, given that the planet receives only 65% of Earth's energy from the Sun. The planet is not very conducive to life, though. Most likely, it is tidally locked, meaning that it faces the star in the same direction all the time, creating everlasting day and night sides with notable temperature variations. Because of its proximity to Proxima Centauri, the planet also receives 100 times as much high-energy radiation as Earth, including ultraviolet and X-ray light. During star flare-ups, Proxima b gets pounded by high-energy particles. Unless it has a shielding magnetic field like Earth's, these conditions may be hazardous to any potential life forms. This world could be more welcoming under some actual circumstances. According to models, the freezing off of volatile gases on the night side may cause the atmosphere of tidally locked planets to collapse quickly. Volcanic activity can restore our planet's atmosphere, while planets with strong magnetic fields are less likely to lose their atmosphere. However, we are unable to even speculate as to whether or not Proxima b has an atmosphere due to our lack of knowledge regarding the planet's magnetic field strength or volcanic activity. Still, scientists are eager to find out if Proxima b harbors a highly developed civilization since an atmosphere requires seas, and both conditions together require life. The night side, which would otherwise be too chilly and dark for acceptable habitation, may be lit and heated by energy produced by solar panels covering the day side. A race has begun to ascertain if Proxima b crosses the face of its star as viewed from Earth in response to its discovery. Scientists would be able to compute the planet's density once they had established the planet's mass and size through these transits. Finding the density would confirm that the planet is made of rocks and reveal what resources were employed to manufacture those rocks. Starlight may flow through the planet's atmosphere during a transit, revealing the planet's makeup. But only 1.5% of the time will the orbit be in the proper alignment for scientists to see a transit. Complicating matters is the star's tendency to flare. A rocky planet absorbs sunlight and re-emits it as infrared radiation due to the star's heat, according to Columbia University astronomer David Kipping. But stars like Proxima Centauri emit a different kind of infrared radiation from rocky worlds. Fortunately, infrared light research is the primary purpose of the James Webb Space Telescope. The infrared heat signature of Proxima b is essential for determining the planet's atmosphere. Furthermore, Hubble's successor has a significant affinity for the infrared region of the spectrum. Even at night, Proxima b's city lights will be visible to the James Webb Space Telescope, even if they are as dim as those that our civilization uses on Earth. If artificial light is limited to a frequency range that is 1,000 times narrower than that of starlight, Webb may detect it. Because Proxima b has special spectral edges that reflect starlight, its day side is thickly covered in solar panels. The day and night are the same as Proxima b circles around its star. Cold nighttime lows come after midday highs. However, the variation in temperature between day and night depends on whether the planet is constituted of all exposed rock. Heat is conducted by the water and the atmosphere. Put another way, Proxima b's dayside and nightside temperatures will vary more if there is an atmosphere there. An atmosphere is assumed to exist if the variation in temperature between day and night is not as great. Conveniently, after Proxima b successfully completes its orbit around the star, the JWST will only need 112 Earth days to measure the infrared radiation from its two faces. If Proxima b has an atmosphere, the next stage will be to examine its composition. Particularly, the presence of gases such as oxygen, water vapor, and methane may suggest the possibility of livable conditions, if not real living things. But in order to do this, we have to collect starlight, a very challenging task, as it passes through the planet's atmosphere or bounces off of it. Unfortunately, because Webb was not designed to search for extraterrestrial life, it is only able to closely analyze a small number of the closest potentially habitable worlds. It is also restricted to monitoring variations in the atmospheric quantities of water vapor, carbon dioxide, and methane. Webb is not able to identify the strongest indicator of life, unbonded oxygen, even though certain combinations of these gases may indicate the presence of life. The extremely large telescope is one of the planned ground-based observatories that will be able to do an extensive atmospheric examination. It is expected to start operating in the middle of the 2020s. One of the substances that the JWST could be able to find is ozone. The data from the JWST may be useful for 10 years from now, if those telescopes remain in service. Advanced methods may be used by even more potent space telescopes to hide the dazzling luminosity of a planet's parent star and reveal light reflected back from the planet. If you want to see farther away, try doing things like covering the lights with your hand. This could be accomplished by big external umbrella-shaped satellites or tiny interior masks in space telescopes of the future. It is significantly simpler to investigate light reflected off a planet once starlight has been suppressed. Regretfully, non-biological forces can also produce most of the gases released by terrestrial life. For example, methane is a gas released by both volcanoes and cows. Photosynthesis is the process by which sunlight converts water molecules into oxygen and hydrogen. Astronomers will undoubtedly encounter some false positives in their search for extraterrestrial life. To determine whether a planet of interest geology or atmospheric processes might resemble a biosignature, which helps rule out false positives, they need to have a complete grasp of the world. The next generation of exoplanet studies could yield the strong proof needed to prove that life exists. The initial data from the James Webb Space Telescope provides us with a sneak peek at the major breakthroughs that are yet to come. One of the most important problems facing science is whether life exists elsewhere in the universe. It's feasible that life exists in large quantities throughout the universe, or it could be that we are the only species stuck on a lonely planet in deep space. In either case, the final answer will probably require considerable philosophical and psychological changes on the part of the participants. We appreciate you tuning in to another Space Theory episode. For more incredible space videos, click the video on your screen while you're still here.